Yongzheng Sun, who will be telling us about quantifying the resilience of coal energy supply in China towards carbon neutrality.
Thank you. My name is Yongzheng Sun from China. I have a short English name. You can call me Sunny. Today, I'm happy to here to introduce our recent work on the resilience of the coal energy supply in China toward carbon neutrality. You know, my university is mining and technology, most focused on the coal mining technology. And facing the challenge of global warming and the pollution problem, China in 2020, China announced to cut its net carbon emission to zero by 2020 and reach the peak at 2030. In order to achieve this goal, China has taken a lot of measures focused on the develop the clean energy technology. In 2025, China has added 400 GW of wind and solar energy. Now, the share of the new energy increase and the future and the fossil energy has lost its share. And it was reported that China carbon emission may have peaked in this year. And so, as in the past, the coal is the main energy source of China. But as you know, the new energy, if we depend mainly on the new energy, for example, we depend on the solar and on the wind, but this is not accountable because the coal mining is, because in China, this new energy has been affected by many factors. So it's very important to investigate the resilience of the energy market of China. In order to achieve the carbon neutrality, China has taken many actions. These actions, I think, has important impact on the energy market. So here we want to focus on the resilience of China's coal energy supply. What is resilience? Resilience is an older term. Usually, in ecology, it shows the ability for system to maintain its structure and energy after has been perturbation. There are a lot of research about resilience, such as the resilience of the society, resilience of the work, resilience of financial networks. Even there are some research about the resilience of the energy systems. Here, we focus on the resilience of the China's coal energy supply market. In this paper, from the viewpoint of network science, we built a mathematical model and to quantify the resilience of the coal energy supply in China. This is our model. Here are air. We assume that there are many coal mines. In fact, in China, there are more than 2,000 coal mines, but most are small coal mines. Here we only show 100 biggest coal mines. These biggest coal mines accounts for more than 90% of the coal supply in China. First, we built the networks. We think if the two coal mines, they supply coal to the same power plant, we think there is a link between the two coal mines. So there is a network. This is based on the transaction data between the coal mines and the power plant. And our model contained here R is production of the coal mine I. And here is two parts. The first term represents the self-dynamic of each coal mine. It's a logistical growth. And the second part to represent the interactions between two coal mines. If there is a link, we think there is a competing competitive interactions between the coal mines. And because we want to get some theoretical result, so we map the high-dimensional original networks to the 1D systems. Here we use the mean field method. From this equation 4, we get this 1D model. From this way, we can use some mathematical theory. We can find for this 1D system, we can find if we choose eta. What is eta? Eta is theta times beta is eta. As a bifurcation parameter, we can see there is a critical point, eta, effective eta C. And this critical point depend on the structure of networks and the dynamics of the coal mines. So we can investigate what is a factor impact the resilience of the coal market. As we can see for the 1D system, if the eta is less than eta C, then there are 3 steady states, and one is the stable state. This is the unstable state, and they still have the zero equilibrium. Zero equilibrium means that if the system tends to this zero, it means that the loss of resilience. So in order to verify our theoretical result, we do some simulations. First, we show what is, we focus on the influence of the network topology. We can see that as an increase of the connectivity, we can see the eta increase. And when the eta cross the critical value, we can see from the figure that there is a loss of the resilience with property 1. And we also investigate the impact of network size and the modularity and the local connectivity. From here, we can see that if the networks has more modulars, so it is a high resilient state. And here we also show some shock on the networks. We consider 3 cases. One is we delete some nodes. Delete some nodes from networks means close some coal mines. In fact, in China, China government want to control the use of the coal. So they close many small coal mines. From this figure, we can say if we close more small coal mines and the REFF have high value, so we can say that close small coal mines is an effective method to improve the resilience of the networks. And we also show the effect of to delete some link. Delete some link means that because in China is very large. So maybe one coal mines in the west part, they will ship this or by train to let this coal to the east part. So there are a lot of links. If the government want to limit the long distance transaction, so we can see that the resilience of the whole network will improve. And finally, we verify our results, use the real networks. Here we can, firstly, we show that the degree distribution of the China coal market networks. We can see this is not the normal distribution. This is someone called it it's similar to the scale-free degree distribution. And from this figure, we can see there is a structure of the modularity. So we find that this kind of structure can improve the resilience of the coal market networks. We also to show some real policy, or we want to give some policy suggestion. From this figure, we can show that if we close some small coal mines, it can improve the resilience. And here it's just I mentioned, we limit the long distance transaction. And also we can find that all this resilience stat has been captured by the 1D system. From here, we can see that the 1D system, they have the bifurcation figure. This bifurcation figure, we call this resilience function. There are many perturbations, but for each perturbations, the steady state will located in this 1D resilience function. So finally, we consider the impact of the neutrality, zero neutrality. In China, they say we want to achieve the zero carbon neutrality in 2060 and reach the peak at 2030. In fact, as I show in the report of the economics, they said that China has reached a peak in this year. So we consider several scenarios. The one is the peak 20. Peak 20 means that we reach the peak as the 2020, peak 25, peak 30. This all the scenarios data from this this paper. Because in different scenarios, they give the estimation of the energy supply by coal in the future. And we use this data to our model. We can see that if we want to achieve the goal earlier, and we have the negative impact on the coal mines supply. So that's the main idea. Thank you. This is our co-authors. Thank you.